Hello guys, welcome back to Brooks of Math. I'm going to go over the 2006 Aime Ii number 14. So let S sub n be the sum of the reciprocals of the non-zero digits of the integers from 1 to 10 to the n inclusive. Find the smallest positive integer for which it's an integer, S sub n. Okay, first of all, S sub 1, what would that be? 1 over 1 plus 1 over 2 until 10 to the 1, right? But it's the sum of the reciprocals of the non-zero digits. So it would be after 9 for 10, we would only have 1, not 0. So it would be plus 1 over 1 again. What about S sub 2? Now that's just all of that. And then we would have 1 over 11, which is 1 over 1 plus 1 over 2. And then for 12 we would have 1 over 1 and 1 over 2. And then 13 1 over 1 plus 1 over 3 and so on. For 1 over 100, since it's S sub 2, it's until 10 to the 2. So 1 over 1 again. And this basically repeats. The first thing you would notice, so the first, this has the same first 10 terms as this, because it includes the integers from 1 to 10, for example. Also, since this includes the first digits that are non-zero, it cycles those digits over and over again and repeats them. So for if we have n equaling 1, that gives us the reciprocals of the digits from 1 to 9 and an additional reciprocal of 1, which is just adding 1. When n equals 2, we have 10 times as many. We have 10 times these. So 10 times the reciprocals from 1 to 9. And then an additional 1 like before, right? So we actually not really. I'll talk about that after. So first we would have like 1 through 10, right? Then 10 through 20 or 11 through 20. And the first digits of these, they're the same every single 10. So they repeat 10 times. So 1 through 10 until 91 through 100. Okay. And the tens digits of these, we would have 10 of these which have a tens digit of 1, 10 of these with tens digits of 2, and so on. So it doesn't matter which digit place they are. It's still going to be another set of reciprocals from 1 through 9. 10 of them, actually. And then an extra 1. Okay, n equals 3. Okay. So we would have 1 through 1,000, right? Actually, let's express this in terms of this previous sum now. For n equals 2, for example, we had 10, since we have 10 times as many numbers, we have 10 times the previous sum. Sorry. And then we had an additional, for each of these 10 digits, we have 10 of these each. So 10 times each of these reciprocals, which makes 10 S1 again. And then another 1 for the 100, that last number. Okay. In the same logic, in the same way, S sub 3 is equal to, we have instead, in terms of S sub 2, so we have 10 times as many numbers which loops all of these reciprocals, like for the numbers until 100, from 101 to 200, and so on until 901 to 1000. And then in addition to that, we have a new digit, the hundreds digit. So like we have 100 of each of those. So we would have 100 of 1/1 for the hundreds, and then for 200s we have 100 of 1/2, and so on, just like before. So we would have 100 of the reciprocals from 1 to 9. And since this term appears so often, let's give it a variable. Let me clear up that space. If we let x equal 1 plus 1/2, 1 is just 1/1, by the way. So yeah, the sum of reciprocals, let it be x. So then we would have S1 is just x plus 1. S2 is, in terms of S1, we have 20 S1 because for the tens digits and the ones digit being repeated 10 times. Both of them are actually. So 20 S1. S3 is equal to, so over here, we have 10 times S sub 2, and then because 10 100s, and then 100 times the reciprocals from 1 through 9. And then with the extra 1 for that 1000, the last number. So it would be 10 S2 Oh, sorry. S1 includes this extra 1, so it would be much more accurate to say 20x. Okay, on the other hand, 20s2, 20s2. Wait. Okay. So for n equals 2, we have 10 of these, and then 10 of those, and then the 1, which is 20x plus 2. That's true. Okay, for S3, we have, well, we have S2 minus this 1, which is, yeah, that's what we're doing. We have S2 minus this 1. So 10 times, for 10 of each 10 of the hundreds, S2 minus 1. And then, for each of the hundreds, yeah, we have 100 of those, and then that extra 1. And actually, if you look closer at S2, what this actually is we have 10 S sub 1 minus 1 plus 10. That's how we got it, x plus 1. And it's very easy to see that this pattern continues indefinitely. Okay, now that we have that, a clear picture of the sums, let's see whether we can simplify this. Since we have these ones, what if we just define a second sequence? Since this is a number 14 after all, we can t sub n equals s sub n minus 1. Okay, then it would be simplified, so t sub 1 plus x, t sub the second term is going to be 10 times, so this is 10, just 10 t sub 1 minus, wait, plus 10x plus 1, but it's minus 1. We don't have the extra 1 since this is the new series. And t3 is going to be 10 t2 plus 100x. Let's actually make it x squared, and this is x of 1. Sorry, x. And this continues like that. So t sub 4, for example, would be 10 t sub 3 plus 10 to the 10 cubed x. Okay. So, well, if we express this as something else, okay. T sub 1 is x. Okay, t sub 2. Well, t sub 1 is x, right? So this is, you get, well, if you write an explicit formula in terms of x, t sub 2 equals 10x plus 10x, which is 20x. T sub 3 equal 10 times 20x plus 100x. So we get 300x. And if you, in fact, if you compute some value t, if you compute it for different terms, you're always going to find that this is equal to n times 10 to the n minus 1 times x. A really simple formula for it. Because you're adding a 0, yeah, you find out that you're adding a power of 10 each time, and this number gets bigger. So, well, can we inductively prove this? Well, we do have this. Yeah, if you try using induction, if you plug into the recursive formula, which we know is true if you look at our original logic, if you look at the form our logic, that whoa, and 10 so then plus 10 to the, that's why I wrote it in exponential formula, 10 to the n x. This is the formula that seems to hold up. It holds up for the first few terms. So if you actually express it in terms of last, so if this is true, it can only be true if we have if we're adding, well, it can only be true if t n plus 1 is equal to n plus 1 times 10 to the n minus, sorry, 10 to the n x. That's our goal. Okay. So if we're given that, and we plug in our assumed explicit formulas, 10 times 10 times 10 n minus 1 x plus 10 to the n x. And this 10 adds this exponent, it becomes n. Since we have n times 10 to the nx and 10 to the nx, this becomes n plus 1 times 10 to the nx. Okay. And we've just proved inductively that this formula holds. Alright. Now that we know this formula is true for sure, we can use this and go backward. So add, since this t series is 1 less than its corresponding s sub n term, then we found the explicit formula is going to be 10 to the n minus x minus, sorry, plus 1. Okay, now when is this an integer? Well, we know what x is. It's the sum of the first it's the sum of the first 9 reciprocals, or the reciprocals of the first 9 numbers. So for this to be s sub n to be an integer, all we need is for the numerator of a fraction we get. So for this term, for example, it's going to be, this doesn't change whether it's an integer or not, so we can discard it. So basically we need this to be an integer, and it's only an integer when the numerator, or what we're multiplying here, is a multiple of the least common denominator of this. So if we have of 1 through 9. Now it's going to be equal to some number k over the least common denominator of 1 through 9. And what is this actually? Well, okay, we have 1 through 6. Obviously the least common denominator would be 60. You can check that for yourself. Once we add 7, we get 420. Any number. Okay. Once we add 8, wait, 8, okay, 840. Once we add 9, this is already divisible by 10, so we just need another factor of 3. So you would get 2, 520. Okay, that's the LCM of the first 9 or 10 numbers. It's the same LCM. Okay. So our denominator would be minimized as 2520. Meaning this would be a multiple of 2520. So 2520 divides it. Okay. Now, the only two numbers that would divide 10, or the only two primes, would be 2 and 5. But what we need to divide this, or, well, what are the primes less than 10? 2, 5, 7, 2, 3, 5, 7, 2, 3, 5, 7. This is already taken care of. It's already taking care of the 2 and the 5. So this, for this, we would need our 9 and our 7 to divide it, because we have 9 over here, not just 3. So for 2520 to divide this expression, we need both 7 and 9, in turn 63 to divide n. And actually, once it divides n, this will indefinitely divide this, because we have the 2's and 5's dividing into this, since n is really big. So the smallest n in turn is just 63. Thanks for watching, and I hope this helped you.